Okay, so let the recording start. All right. So in the previous lecture, we were discussing the counters. Okay. And we saw one example. We took two flip-flops and we arranged them in a specific manner, and we tried to obtain the timing diagram based on the clock pulse. Okay. And I specified that the counters are classified into basically based on the clock pulse on two types. First is asynchronous counter, that is also called as a ripple counter, and the second is synchronous counter. Okay, and the second category was the states of counting, the method of counting. If it is counting from 0 to upwards, that is up counter. If it is counting from higher value to lower value, descending order, that is down counter. And we can design up and down counter both. So there I made a mistake. For both counter, that is up and down counter, I stated like it can count 1, 4, 6, 2, 3 like that. It is not so. What up and down counter do? There is a mode operation. If we allow that mode to count in a specific order, that is, say if we allow it should count in a up order, up counting. So it will count in a up counter. It will count in up order, and if we allow that it should count in a down order, so it will count in that manner. So that will work as a down counter. Okay. So today we'll see 3-bit. We'll analyze 3-bit up counter, and that is asynchronous counter. Or you can say ripple counter. Okay, be specific for 2-bit. Okay, so in the previous lecture also you saw this diagram. First of all, there are few statements for this counters. If it is a 2-bit counter, so if it is a 2-bit counter, let's suppose we want to design n-bit counter. So how many flip-flops we require? N flip-flop. Okay, and how many states this counter will count? A 2-bit counter or n flip-flop, using an n flip-flop counters, we are making a flip-flop counter using n flip-flop. So how many states it will count? So the states will be state of that counter will be 2 power n, is to n. And what will be the maximum state? Maximum state will be 2 to the power n minus 1. Okay, so when I say 2-bit counter, so it will be 2-bit up counter. So it will start from 0, 0, 0, 1, 1, 0, and 1, 1. So this will be the maximum state. So what is the weightage of this? Weightage of this is 2 to the power 2 minus 1. That is what? 3. Okay, so we have written here the maximum states with n-bit counter or n flip-flops that is using that counter. It can have maximum state, that is 2 raised to power n minus 1, or the total number of states will be 2 power n. Okay, so total states, how many states we have here? S1, S2, S3, and this is S4. And which is 2 to the power n 4 states. Right? Also, the states, total number of states that a counter counts is called mod or modulus. So we can also say this counter as mod 4 counter. So the total number of counting states is also called a modulus of counter. So the question can come in this manner also: design a mod 4 up counter, design a asynchronous mod 4 up counter using JK flip-flop. So it means if it is a mod 4 counter, you require two flip-flops, two JK flip-flops, because mod 4 means what? Mod 4 means it will have 4 states, and for 4 states we require n flip-flops. That is log 2. No. How many states, how many flip-flops require for this? So it will be log base 2 to s to power n. This will be the flip-flops. So this will come out as n. If you have 2 raised to power n states, so it will require n flip-flops. Correct? So now we'll design, or we will analyze a 2-bit up counter, that is asynchronous counter. In today's lecture, we will be only dealing with the asynchronous counter or the ripple counter. From the next class, we'll see the synchronous counter. So what is the definition, or what is the methodology we use for the clock pulse in asynchronous counter? Yeah, output of the first flip-flops is fed as the clock pulse of the next one. Okay, so here I have J0, K0, that is my first flip-flop, and here J1, K1, and this is Q1, and it is a negative age trigger flip-flop, and all of this are connected to high. This is logic 1, and this is also connected to logic 1. And this is your clock pulse, CLK. Now we'll analyze this circuit, and we will find out what is the states this counter is counting. This is my Q0, and this is my Q1. So remember always, whenever we are talking about the ripple counter or the asynchronous counter, the first flip-flop in which the clock pulse is directly applied, that will lead to the LSB. Because we have seen this counter will count 4 states. Okay, so which one will be your Q0 and what will be your Q1? So the output of the flip-flop in which the clock pulse is directly applied, the output of that flip-flop will lead to the LSB bit always. And the reason is that for every clock pulse, this output will change. And here you see, for every clock pulse, this will change. However, the second one, that is a MSB bit, it will change after a time. So it is connected in this manner. The output of the first one is connected to the second one, the clock pulse. So it will take some time. And the time will be the 2 clock pulse. Correct? That is why this one will be MSB. Let's suppose we have 4 counters here. Sorry, 4 flip-flops. So how many states that counter will count with 4 flip-flops? 2 raised to power 4, which is equal to 16. And the MSB bit will be the last one. MSB bit we will get, that will be associated with the last flip-flop. Correct? This is my first flip-flop, or the 0th flip-flop, or this is my first flip-flop. Hold on a second. Okay, now see. So this is my clock pulse. And we have 0 here, and these flip-flops are negative age triggered. So the transition in these flip-flops will occur only at the falling edge of this clock pulse. Now I have this Q0, and initially it was 0, and when the moment it see the negative edge of the clock pulse, it will change the output according to the inputs. And here we have 1 1 at the JK. So JK 1 1, it means it will complement the previous one. Do you remember the truth table of JK flip flop? It will toggle. Okay, so previously if it was 0, we assume that both the states were 0 0. Here Q1 were also 0. So as it sees the negative edge, it will change the output of that flip flop, and it will remain same till the next negative edge. So this manner we can draw. Correct. Now Q1 is what? Q1, the clock pulse of Q1 is connected to the output of this one. So now it will see the negative edge, the falling edge of this Q1. This Q0. Q0 will work as a clock pulse for this second flip flop. Now, so for till the negative edge, it will remain 0. Then it will complement the previous one, that is 1 now, and again it will go 0. And again it will become 1. Let me draw how many states we have. This is 0th clock pulse, first clock pulse, second clock pulse, third, fourth, and the fifth. Correct. So now it was 0. Now analyze this. We have clock pulse here, 0, 1, 2, 3, 4, and 5. And what are the states of this counter? So for the 0th clock pulse, it was 0 0. For the first clock pulse, the output will be 1 and 0. So what is 1? Q0. Q0 is 1 and Q1 is 0. In the second clock pulse, the output is 0 and 1. So it will become 1 and 0. In the next clock pulse, that is third clock pulse, it will become 1 and 1. So this is 1 and 1. Here for the fourth clock pulse, both will be 0. Q0 and Q1 are 0 0. And for the fifth clock pulse, again you see Q0 is 1 and Q1 is 0. So if you can analyze this this table, you can see we have repeated after four states. 0 0, then 0 1, then 1 0, then 1 1. Then after 1 1, what we obtained at the output of these flip flops? 0 0. Isn't it? And then 0 1. So this circuitry or this sequential circuit is counting the states. For the 0th clock pulse, we have 0. For the first clock pulse, we have 1, then 2, 3, and then 0, 1, 2, 3, and so on. So the total states of this flip-flop is 4. No, 2-bit. is 4. Now see, what is the frequency of this clock pulse? Let me define the time period. So when it repeats, we can start from this point. So this will be the time period, because here the clock pulse has the negative edge. Again, here it has a negative edge. Means this pattern is repeating after this much time. So what is the time period of this clock pulse? Let's suppose t. Okay. So the clock pulse has the time period which is equal to t. And what will be the frequency of this clock pulse? The frequency of this clock pulse will be 1 by t. Do you know this relationship between between the time period and the frequency? The frequency will be 1 by t. Now observe this q0. And what is the time period of this? So time period of this will be this much, and which is exactly equal to double of this one, double of t. So time period of the first flip-flop zeroth flip-flop will be 2t. And what will be the frequency of this? Frequency will be what? 1 upon 2t. So let me call this frequency as fc. And how can we relate this fa? If this circuit, this flip-flop has a frequency at the output which is equal to fa, so how can we relate this one? So fa will be fc by 2. See this, is it true? Is it correct or not? Yes, this is correct. So we have divided the frequency at the output of this first flip-flop. And for the second one, if you can observe here, this is the time period. And which is the fourth time to the clock pulse of the time period of the clock pulse, isn't it? So my FB will be what? FB will be FC by 4. So we also call a flip-flop as a frequency divider. Divide by 2 circuit. This flip-flop is also called a divide by 2 circuit. Which divides the frequency. So if the frequency of this clock pulse is fc, so frequency of this output or the output of this flip-flop will be fc by 2. And if this flip-flop is connected in the previous manner, in the asynchronous manner, so again we have frequency division here, that will be fc by 2 whole by 2. That will be equal to what? fc by 4. And if you can see here, I can write this fc by 4 as 2 power 2. And 2 here is the number of flip-flops, isn't it? So if question comes, there are 3 flip-flops in the counter and the counter is counting upwards, it is 3-bit up counter. So what will be the frequency at the output of the last one? fc by 2 to the power 3. This will, isn't it? Okay. Now what happened if I connect the clock pulse in this manner? I have this two flip-flops J and K, and now clock pulse is connected from the Q bar. This is what? This is Q bar. So this J0 and K0 both are high. J1, K1 both are high. High means they are fed as logic 1, and now clock pulse is connected in this manner. The complement output of the first one is connected at the clock pulse of the second one. Now try to analyze what happened. So I have this clock pulse. Okay, see there. Whenever there is a clock and the moment it sees the negative edge, the output of the first flip-flop will change. And now we have this Q0. Okay, but the second flip-flop will not change according to this. It will change according to Q bar. Okay, and for the negative edge. So we can say for the positive edge for this Q1, Q0, isn't it? No. So let me draw this Q bar. What will be the Q bar? Q bar will be high, then 0, then again high. It is just complement of Q0, nothing else. Isn't it? We have 0 here, so Q bar will be Q0 bar will be 1. Then for 1 it will be 0. For 0 it will be 1, 1, 0, 0, 1, 1, 0. So now we want to analyze Q1. We'll see Q1. What will be Q1? See this. Whenever there is a negative edge in the Q0 bar, it will change the output. So previously if it was 0, now it will become 1. Isn't it? अरे समझो ना, सेकेंड फ्लिप फ्लॉप जो है वहां पे जो क्लॉक पल्स लगा हुआ है वो ये क्लॉक पल्स है. सो इसी को फॉलो करेगा. Output of this second flip flop, that is Q1 here, we are talking for this, and this is Q0. So whenever it sees negative clock pulse, negative edge trigger edge at the Q0 bar, it will change it. It will change the previous one. It was 0, so it will become 1 now. Now here for the next one, it will remain 1 till the next negative edge. Now it will become so it will again change here. Now for that counter, we want to analyze what are the states. So this will be definitely my LSB because we have applied the clock pulse directly to this flip-flop. So output of this flip-flop will lead to the LSB of the states. And here this will be my MSB. So for the 0th clock pulse, what is the output? For the 0th clock pulse, what is the output? 0, 0. Because we are not observing Q bar. Sorry, Q0 bar. We are observing Q0. So 0 for this one, it will be 0. Q0 will be 0 because Q bar is 1. The next one will be what? The first clock pulse will be 1, 1. Okay. The next one, Q0 will be 0 and this will be 1. And this will be for second, and the for third clock pulse, where are we? Q0 will be 1 and this will be 0. And again we have 0 and 0 for the fourth clock pulse. So you can see here the states are, the weightage of these states are what? 0, this is 1, this is 3, 2, 1, 0. So now my counter has started counting in descending order, isn't it? So if we change the clock pulse of the second one, we can change the type of the counter. The previous one we have applied Q0 as the clock pulse to the next one. For this we have applied Q0 bar as the clock pulse to the next one. And now it has started counting as a down counter. So we will define this counter as down counter. This is 2-bit. What is this? 2-bit asynchronous down counter. Okay, so now it is clear. If I want to count in upward direction in the ascending order, I will connect this Q0 as the clock pulse of the next one. And if I want a down counter, so I will connect Q bar as the clock pulse. Now what? Now see, there is a property of XOR gate. What is that property? What I want here, I want a combinational circuit in between these flip-flops that can say, I will decide my mode here. Now I will say if M is equal to 0, so this combinational circuit should be operating in this manner. So this counter will operate in ascending order. So it will become a up counter. Or if I say M is equal to 1, so this counter should count in descending order, that is down counter. So I want to design a combinational circuit in between these two flip-flops so that we can connect the clock pulse to the next one. And that will become a up/down counter. Correct? So there is a property of XOR gate. What is that property? If I say this is my mode, and according to mode, I want to change the operation of this, and I have here Q, that is the output of this flip-flops. So these are if the two variables, so what will be the output of, and these inputs are fed at the XOR gate. So what will be the output of XOR gate? Zero, 1, 1, 0. Okay, so see here, when my aim is 0, so it is replicating, or it is reflecting the Q. Whatever the value of Q we have at the output of XOR gate. When my aim is 1, there is a complement of the Q at the output of the XOR gate. Isn't it? Is it clear? When we have M equal to 1, so at the output of this XOR gate is what? Complement of Q. And that we need for the down counter. What we need? We need the complement of the output of the previous one. So now see, if I can arrange this in this manner, I use one XOR gate, and now I connect here with this. This is my mode. and this is Q0, clock pulse, both J and K are high. This is J1, K1, and Q1, and this is connected to the clock pulse of the second one. So see the operation of this. Analyze this circuit. Try to analyze this circuit. When I say M is equal to 0, it means, I just roughed it. M is equal to 0. M is equal to 0 means the output of this will be what? Q naught. Because it will reflect whatever the input of the second input of the XOR gate. So now when M is equal to 0, it will be the Q naught will be at the output of this XOR gate. It means we have connected Q naught as the clock pulse of the next one. So that circuit will fulfill and it will start counting in ascending order. Correct? So this circuit will become up count. When M is equal to 1, so what will happen? The output of XOR gate will be what? The complement of the Q, and that we need for the down counting. This is what? Q bar is what? Just complement of Q naught. So instead of connecting wire from here, we can just connect one XOR gate and we give one mod input as the input of this XOR gate, and we can have one up down counter. And this is your up down counter, 2-bit. Okay, ये तो हुआ 2 bits के लिए. Whenever we want for 3 bits, 4 bits, will it be easy for you? Can you do it? Whenever there is a question, design 3-bit up counter, 3-bit asynchronous counter or the ripple counter. Only 3-bit up counter. So what will you do? You just put one more flip-flop and connect this output of the Q1 to the clock pulse of the next one. Okay. Okay, there may be some different logic circuitry here that can be used for the converter of this up and down counter. We can see that. We will see here. See, we have one mode operation and we have this Q and Q bar. Okay. And what I want at this point, okay, see, I will use the next circuit, and I want to design a logic, combinational logic here that can feed the clock pulse of the next one. Okay, and that is my Y. One way we have seen we can use the XOR gate, and that is very easy. But easy questions don't come in the question paper. They will give a different circuitry and they will ask, what is this? Okay, so we want to design one combinational circuit here that can work as an up and down counter. With what? We have one mod input and we have this Q and Q bar. So these three are the inputs for this combinational circuit, and we want to design and we want to obtain Y that can work according to this up and down counter. Okay, how will we proceed? So we have this 3 variables. So there will be total 8 combinations. Correct. Whenever my M is 0, as a designer, I have said it should count in ascending order. So it should work as a up counter. So up counter means what? This Y should be what? Y should be just directly Q. Y should be Q. That is my previous output, the output of the previous flip-flop for the up counter. See their diagram, isn't it? So in this circuitry, in this combinational circuit, I want to design this Y, and when M is equal to 0, so this will be counting in this manner, so it will work up counter, and for up counter, the next clock pulse, the clock pulse for the next flip-flop will be Y, sorry, Q0, isn't it? So this Q0 will be my output. Okay. When I applied 1 as a mode, so the counter will work as a down counter. So the clock pulse will be connected to Q bar. This will be my output. Now write a CAM app. It will have 8 cells as 3 variable, 0, 1, 0, 0, 0, 1, 1, 0, and 1, 1. Okay, so this is my 0, 0, 1, 1, 0, 1, 1, 0, isn't it? So how will you group this? There can be 3 implicants, but the essential or the prime will be this. Okay, so what is this? This is my M Q bar plus M bar. This is capital M. So capital M bar Q. Is it clear? Okay, so I can have two NOT gate, sorry, two AND gate. They should be complement to each other. यही ना क्वेश्चन है. ये क्वेश्चन मुझे भी आज तक क्लियर नहीं हुआ. मैं चाह रहा था कि you will not ask this question, but I will find out the answer and then I will answer you. But this is the way we can design this. Actually, कुछ तो उसका होगा logic. I will find out and I will tell you. Okay, so first, the input of this first AND gate will be what? M and Q bar, or we can take that one. So this is my M line, and we have NOT gate. So M bar and Q, and here what we have? M and Q bar. So you can connect this way. And one OR gate. So now this circuit will also work as a up-down counter. And what will be the output state? This. You will be observing this one. And this Q0 will be what? LSB, and this will be MSB. You can check. Let me check. When I say M equal to 1, M equal to 1, it means this is 0. No, this is 0, because we have connected to M bar. So 0 means we have 0 here, and this is connected M equal to 1. So whatever the second input that will come here, that is Q0 bar, and Q0 bar plus 0 is equal to Q0 bar. So we will complete this circuitry. So here we have Q0 bar. And when I say M is equal to 1, it should count in this manner, that is down counter. So we have fulfilled our purpose. Isn't it? And when you apply M equal to 0, so for 0, this AND gate will result as a Q0, and here you have 0. So the Q0 will be connected to the clock pulse of the next flip-flop. Okay, so with this, we stop this lecture here. And today also I forget to obtain your attendance.